Good day everyone and welcome to another lecture. We are now on lesson 7 entitled Extent, Yield, Conversion, and Selectivity. This signals our transition to dealing with material balance problems involving chemical reactions. Okay, so let's begin. Let's first start with some key things to remember or some key things to recall. So as I have said, this marks the beginning of incorporating chemical reactions in material balances because previously we have limited ourselves to performing material balances without chemical reactions. So these are just some key things to remember. First, the generic name to a unit involving chemical reactions is a reactor because its main purpose is to react your reactants and produce a product. But the term reactor is very generic. We can actually use more specific terms such as burner, oxidizer, and other things. No? But for simplicity purposes, we can use reactor as the name of our unit here. Second, mass is still conserved. The total mass input is equal to the total mass output for all steady-state processes. We are still dealing with processes that conserve mass from inputs to the output for steady-state processes. So your total mass inputs would still be equal to your total mass output even if you had a chemical reaction or even if you had a change in the components of your feed. However, for the third one, the volume and the total number of moles may not be conserved due to the nature of chemical reactions. This is very true because not all chemical reactions have the same number of moles for their input and their outputs. No? This is especially true for gaseous reactions. There could be a change in volume and there could certainly be a change in the number of moles from your reactants to your product. So it's not advisable for you to be performing an overall material balance using moles. From this point forward, it's only advisable to perform the OMB for mass. No? So it's an overall mass balance. Next. Okay, for this one, we have to strengthen your foundation of stoichiometry. You have to review some key concepts of stoichiometry. Well, first and foremost, you have to review how to perform stoichiometry. If you're given a balance equation, how do you then perform calculations in relating the amount of the reactants to the amount of products or vice versa? And that's because stoichiometric calculations are dependent on the balanced chemical equations. You have to learn or you have to review how to balance equations, and you also have to review how to spot an unbalanced equation because in our lesson, if you did not balance your chemical equation before proceeding with the calculations, then you are already incorrect. Okay? Another good point is that not all reactions go to completion. These are what we call incomplete reactions. Incomplete reactions happen when you do not fully convert your reactants to the products for some different reasons. For this one, we have to review percent yield and the nature of incomplete reactions. And the last one is not all reactants are consumed. This is pertaining to you having to review the concept of the limiting and excess reactants. In the industrial setting, it's actually very, very common for the reactions to not consume all of the reactants. So the review of the limiting and excess reactants would be very important. Now, before we go any further, let's give a little bit preview on how is the material balance process different from our previous experience for those without chemical reactions. So let us imagine a reactor. And we will be representing it as a simple single unit process. It's a reactor with a feed and with a product. Now, since we are dealing with a unit with a chemical reaction, let us write a hypothetical chemical reaction. A plus B yields C plus D. No? So in this case, A and B are our reactants, and then C and D are our products. Of course, in terms of you deciding what's the feed and what's the product, the reactants would be part of the feed, and the products in the chemical reaction would be part of the product of the reactor. So let's right here, we have A and B at the reactant side. We have C and D at the product side. This is a basic overview of a diagram of a material balance problem with chemical reaction. However, this is not always the case because your reactants may not be the only substances that are in your feed. Oftentimes, you can also find inert substances in your feed. So in this case, inert substances are those that do not participate in the chemical reaction. Let's say, for example, we will be adding I, no? So I is not a reactant nor a product, and it's not being converted. So it's an inert. If you find an inert in your feed, of course, you also need to have an inerts in your product side because whatever's going into your reactor should also be going out. And since the inert is not being reacted or is not being consumed, it should still go out of the product. Okay? The presence of the inerts in your feed could lead to some interesting material balances because your inert here could be your tie component, or the inert is the component where you can perform your first balance, no? Because it's a tie component. Another thing that you should consider is that, as I have mentioned earlier, not all reactants will be turned into products. So there might be some inefficiency with the machine, or there could be some thermodynamic difficulty for this process. This might not be thermodynamically viable. So in some cases, you could also see some of your reactants going out of your products. This is a sign that you have an incomplete reaction. Of course, for an incomplete reaction, what that entails is that we were not able to use up all of our reactants, which in this case is A and B. So in order for us to honor the law of conservation of mass, the remaining A and B, or the unreacted reactants, should also go out of the products. So if you take a look at the anatomy of your products, you have a combination of your products from the chemical reaction. That is your C and your D. If you have an inert in the reactants, you should also have an inert in the product. And it's also possible, especially if you have an incomplete reaction, to have A and B, or the reactants, going out of your product. This is the basic anatomy of a material balance problem with chemical reaction. So you should be seeing this in most of our examples later. Let's proceed. Okay, first one. Let's examine the concept of the limiting reactants. So you already know this from general chemistry, that in a certain chemical reaction, if you have more than one reactant, then most probably you will be encountering a limiting reactant and an excess reactant. Okay? The limiting reactant dictates the limiting reactant dictates the maximum amount of products that can be formed. The limiting reactant is also the basis of the theoretical amounts. Take note of this value, no? We will be representing it with N theo. We define this as the maximum amount of products that can be produced from a certain amount of reactants, or the maximum amount of reactants consumed. To illustrate that concept, let's try to solve this example. What is the theoretical amount of ammonia that can be produced by reacting 28 grams of nitrogen and 8 grams of hydrogen? So our given, 28 grams nitrogen, 8 grams hydrogen. And we are asking, what is the theoretical amount of ammonia that can be produced? Or technically speaking, we are solving for the value of N theo. Now in this case, it's important that you know this chemical reaction. This is a very basic chemical reaction, the combination of nitrogen gas and hydrogen gas to form ammonia. This is one of the most common, or one of the most prevalent industrial chemical reactions. First, before we dive into the solving of this problem, you always have to take a look at your chemical equation and make sure that it's balanced before you proceed with doing anything else. So in this case, to balance, we have to multiply this by 2 and we have to multiply hydrogen by 3. So we now have a balanced equation. Okay, next, let's solve for the required. In order for us to solve for the theoretical amount of ammonia, you first have to determine which is the limiting reactant. You have two reactants here, nitrogen gas and hydrogen gas, and you can use the classic method of determining for the limiting reactants by determining how much product do you get from the two reactants. And whichever produces the lowest product is the limiting reactant. So let's begin. Let's start with nitrogen. You have 28 grams of nitrogen. We want to know how much ammonia can be produced from 28 grams of nitrogen. So let's begin the stoichiometry. First, we use the molecular weight of nitrogen, which is 28 grams per mole. And then we utilize the coefficients of the balance equation. Our coefficients are 1 mole of nitrogen is equivalent to 2 moles of ammonia. Solving. By the way, it's not necessary for us to convert the number of moles of ammonia to mass of ammonia because N-theo almost always pertains to number of moles. So remember that, unless it's otherwise specified in the problem. So this is simply 28 divided by 28 is 1 times 2 is 2. So we are producing 2 moles of ammonia coming from 28 grams of nitrogen. Next, we do the same process for hydrogen. So we start with 8 grams of hydrogen. The molecular weight of hydrogen is 2 grams per mole. And then the coefficients from the balance equation, we have 3 moles of hydrogen per 2 moles of ammonia. Solving. This is 8 divided by 2 times 2 divided by 3. We have 2.67 moles of ammonia. Now you have to compare the amount of ammonia produced starting from the two reactants. So it's quite obvious that nitrogen here produced the least or the lesser amount of product, which suggests that nitrogen is our limiting reactant and hydrogen is our excess reactant. Again, this is just a review. We are not yet incorporating this into the material balance problem itself. The question is, what is the theoretical amount of ammonia that can be produced? So as I've said, you take a look at which is the limiting reactant, and then you take a look at how much product was produced. Therefore, the number of moles or the theoretical number of moles of ammonia is 2 moles. It's the minimum amount resulting from our calculations. So remember that the theoretical amount is always related to the limiting reactant and not to the excess reactant. So by the way, significant figures. Okay, we need 3. So this should be 2.00. Okay. Next. Okay, next, we have the percent excess. Previously, we have the N-theo or the theoretical amount of the product that can be produced, which is based from the limiting reactants. Now, the percent excess is based on the excess reactant. Okay, we have the formula here. Percent excess is equal to the number of moles of the excess reactant in the feed minus the number of moles of excess reactants theoretical divided by the number of moles of excess reactants theoretical. We can also solve for the N-theo or the number of moles of theoretical amount of the reactant consumed for the excess reactants. So we have the same example. What is the percent excess of the excess reactants in the previous example. Just to recap, in the previous example, we have 28 grams of nitrogen. We have 8 grams of hydrogen. These are the feed to the reactants. So I am now representing this as a material balance problem, no? And our product, we have found that we have 2 moles of ammonia. Now, we know that all of your nitrogen has been consumed because it's the limiting reactant. So let's denote here. The nitrogen is the limiting reactant, so it has been totally consumed. Hydrogen is your excess reactant. So therefore, we expect to have some hydrogen at your product because it's not all consumed, no? By the way, it's always the nature of the excess reactant to be present in the product for complete reactions. For incomplete reactions, both reactants would still be present on the products. Okay, so let me write the formula for percent excess. This is the number of moles fed minus the number of moles theo over the number of moles theo. Now, the problem pertains to hydrogen. All of the parameters in this equation for the percent excess would always pertain to hydrogen. So this is number of moles of hydrogen fed. This is number of moles of hydrogen theoretical. So we already know the number of moles of hydrogen fed. That is the 8 grams of hydrogen. We just have to convert that to moles. And we have to solve for the number of moles of hydrogen that's theoretically required for the reaction. To recap, our chemical equation is nitrogen plus 3 hydrogen yields 2 ammonia. So let's first determine our N fed. For our number of moles of hydrogen fed, you simply convert 8 grams of hydrogen to moles by dividing it with its molecular weight. Our answer is 4 moles hydrogen fed. Okay, we're done with that. Next, we determine how much hydrogen was needed theoretically. So we solve for N theo. Where do we start with this? For N theo, if you're pertaining to one of your excess reactants, you always start with the amount of your limiting reactants. So we start with 28 grams of nitrogen. We convert this to moles, so we divide this by its molecular weight, 28 grams per mole. We then perform stoichiometry to relate the amount of nitrogen to the amount of hydrogen that is needed for the chemical equation or for the chemical reaction. So in the balance equation, our equivalence is 1 mole of nitrogen is equivalent to 3 moles of hydrogen. Solving, this is 3 moles hydrogen, theo. Okay, so we now have the number of moles of hydrogen fed. We also now have the number of moles of hydrogen that's theoretically needed. You can now substitute those to the equation of percent excess. Okay, solving. The percent excess is 4 minus 3 over 3 times 100%. So we determine our percent excess to be 4 minus 3 over 3 times 100. 33.3%. So our interpretation of this is we have 33% more hydrogen than we theoretically needed, or we are supplying an excess of 33% compared to what we actually needed. In the case of industrial processes, it's actually very common for some reactions to be provided with an excess amount of the excess reactant in order to ensure that the limiting reactant would be consumed efficiently. We will be discussing more on the excess reactant in our discussion on combustion because the percent excess is a very useful figure in combustion processes. Next. Okay, extent of reaction. This extent of reaction is a parameter that tells us the amount of a reactant or product that is consumed or produced. I will be demonstrating how the extent of reaction is interpreted. Consider the example reaction, that's C2H2 plus 2H2 yields C2H6. So let me copy that. C2H2 plus H2 yields C2H6. Now this is not yet balanced, so let's try to balance this reaction. We have 4 hydrogen here, we have 6, so I need to multiply this by 2. The carbon is now balanced, the hydrogen is also now balanced. Okay. So let's try to write the extent balances. So you need to pay attention because the extent of reaction method is one of the main methods that you can use to solve material balance with reaction problems. Okay, imagine that we have a reactor. In the reactor, we have a feed and a product. Our feed, of course, is C2H2 and then H2. And assume that this reaction is incomplete. Our product would contain the main product, C2H6, but it would also contain bits or some unreacted reactants. So we also have C2H2 and H2 in our product stream. Okay? Assume for a moment that the reaction is incomplete. So how do we perform the extent balance? The extent balances are applicable to every components of the process. In this example, we have 3 components, your C2H2, your H2, and your C2H6. Therefore, you can perform 3 extent balances. So I will be illustrating what's the extent balance for C2H2. Okay, so this balance is simply predicated on the conservation of mass. If you will remember, the law of conservation of mass for steady-state processes looks something like this. You have in plus generation is equal to out plus consumption. We added the generation and the consumption in this case because we are now dealing with chemical reactions. The extent balance goes something like this. We want the number of moles of C2H2 that's going out. What's that? This is the amount of C2H2 in the product. C2H2 out. That is equal to the amount of C2H2 that's going in the process. Where do we get this? It's this one in the feed. And then we have plus and minus the coefficients in the balance equation multiplied by the extent of the reaction. Now, how do we decide if we use plus or minus in this second term? It's actually quite easy. You just have to look at the balance equation, and if you simply determine if the species that you are performing the balance is a reactant or a product. We use positive if it is a product because the product is being generated. Remember, here's your generation on the positive side. We use minus if it is a reactant because it's being consumed. This is the consumption. So in the case of C2H2, it is a reactant. Therefore, the sign of the second term in our equation here is minus. So to summarize, the extent balance for C2H2 will now be the number of moles of C2H2 going out is equal to the number of moles of C2H2 going in minus the coefficient of C2H2 in the balance equation is 1. You multiply that with the extent. We have here the extent of reaction balance for C2H2. And you simply repeat the process. You can find the extent of reaction balance for both hydrogen and C2H6. So let's try. Let's perform the H2 balance. So how is our H2 balance here? we need the number of moles of hydrogen going out equal to the number of moles of hydrogen going in. And in terms of the sign, we choose between plus or minus. Hydrogen is a reactant, therefore it's still minus. And then we take a look at the coefficient of hydrogen in the balance equation. That's 2. You multiply that by the extent. So this is minus 2 times extent. This is our hydrogen balance. Last one. I'll go over here. Let's perform the C2H6 balance. It's just the same as the previous balances. The number of moles of C2H6 going out is equal to the number of moles of C2H6 going in. And then is it plus or is it minus? So in this case, it's plus because it's a product. Plus, the coefficient is 1 multiplied by extent. So this is our C2H6 balance. You can liken this with the way that we are balancing components in the previous lessons wherein there's no chemical reaction. So in this case, we are just incorporating the nature of the chemical reaction to the material balance. That's why we are using the extent of the reaction. So you might be asking, what's the unit of the extent? For dimensional homogeneity to be true in this case, if you take a look at this extent balance for C2H2, your units for the number of moles of C2H2 out is moles. The unit for the number of moles in is still moles. So therefore, the unit for extent should also be moles. Another curious thing, so let me erase some of these parts. Another curious thing with this extent of reaction balance is it actually allows you to solve for the value of the extent of the reaction. Now, this is our general rule. For every chemical equation, you only have one value of the extent. And the extent is constant regardless of your balances. So the extent should be the same with your C2H2 balance. The value should also be the same with your H2 balance. It should also be the same with the C2H6 balance. In short, you only have one value for extent for every equation. If you have two equations happening in parallel, then you have two values of the extent. So in this case, let's try to solve for the value of extent. So let's transpose the extent to this side. So we can solve for the extent as the number of moles going in minus the number of moles going out divided by plus minus the coefficient in the balanced equation. This is our formula for extent of reaction. So you can elect to use this. You can also elect to use this. So they are just the same approach. So let's see. Okay, we have here the formula for the extent of reaction. The N sub F there pertains to the number of moles in the feed, so that's your input. The N sub O is your number of moles in the output or out. So that's in minus out divided by the coefficient in the balanced equation. Let's try to solve this problem. If we start with 100 moles of CH4 and 3 moles of O2 in a closed vessel, 0.75 moles of CO2 is produced. Determine the final composition using the extent of reaction balances. So let me first draw the given. Here we have the given. We are given the equation CH4 plus 2O2 yields CO2 plus 2H2O. So this is already a balanced equation. I have drawn this reactor with the feed and the product. We are given 1 mole of methane and 3 moles of oxygen in the feed. We're also given 0.75 moles of CO2 that was formed in the product. Now take note that CO2 is not your only product. Based on the chemical equation, we are also producing water, so that's also in the product. But I am also assuming that this is an incomplete reaction. That's why we also still have CH4 and O2 in the product side. Okay, so the safest way for you is to simply assume that this is an incomplete reaction and you will still have your reactants in your products, or some of your reactants in your products. Okay, that is a safe assumption because if there is no methane and oxygen in the product side, in your calculations it would just appear as 0. Okay, so let's begin. We are required to determine the product composition. Now in this case, for us to determine the product composition, we have to determine how much water, how much methane, and how much oxygen is in the products. So let us name this with variables N1, N2, and N3. So this designation would help us in the building of our balances, of our extent of reaction balances. Okay, so let's begin. Let's go ahead with our extent of reaction balances. The technique here is you first need to determine the extent of reaction, or the value of the extent of reaction, before you can solve all of your unknowns. So of course, you don't start your extent of reaction balance with water because you don't know the amount of water in the product. You would want to start your extent of reaction balance with a component that you already know the amount in the feed and in the products. And in this case, that is CO2. If you take a look at our diagram, there is no CO2 in the feed, therefore the value of N input is 0. There is CO2 on the product, that's 0.75 moles, so you already know its output value. Okay, so we can directly solve for the extent of reaction. Okay, for the CO2 balance, that is output 0.75 is equal to input 0, and then plus or minus. This CO2 is a product, therefore we use plus. The coefficient is 1, so we just have plus 1 times extent, or plus extent. So you see here, since we already know the product value and the feed value for carbon dioxide, we can directly solve for the extent of reaction, which is 0.75 moles. Why did I elect to solve for the value of the extent of reaction first? That's because the extent of reaction is constant for this one equation, and it would appear in all of the other extent of reaction balances. Case in point, let's try to have the CH4 balance. What is our CH4 balance? Output CH4 is N2 based on our diagram. Remember, we have represented the amount of methane coming out of the reactor as N2 is equal to how much methane is going in, that is 1, plus or minus, methane is a reactant, so minus 1 times extent. So that's 1 minus 0.75. N2 now is 0.25 moles. This is CH4. You see, we were able to solve for the amount of methane coming out of the products because we were able to solve for the extent. Let's continue. Let's move on with the oxygen balance. What do we have? Output N3 is equal to input 3 plus or minus. This is minus because oxygen is a reactant. The coefficient is 2 multiplied by the extent of reaction 0.75. So this is 3 minus 1.5, and 3 is 1.5 moles oxygen. Last one, water balance. Output of water is N1. Input of water is 0. There's no water at the feed. And since water is a product, we use plus 2, the coefficient in the balance equation, times the extent, 0.75. Therefore, N1 is 1.5 moles water. In this problem, we had 4 components: CH4, O2, CO2, H2O. we were also able to perform 4 balances, one for each component. And with that, we were able to complete the composition of P. So in your product stream, we have the following components with their corresponding number of moles. So for CO2, that is already given 0.75. For H2O, 1.5. CH4, 0.25. And oxygen, 1.5. Now you can get their percent by mole because it's the requirement of the problem. No? We want the product composition. So I will be leaving to you this solving of the percent by mole. So that is how you perform an extent of reaction balance. Let's proceed. Okay, next parameter that we have to discuss is yield. You are already acquainted with yield. In general chemistry, this is what we call percent yield, no, which is the actual yield over theoretical yield. So in this case, it's still the same. It's still actual yield over theoretical yield times 1000. The only difference is our denominator is now N Theo, which we have discussed earlier. So that's actual yield over N Theo. Next, conversion. Conversion is a very important parameter in your study of chemical engineering calculations because conversions will always apply whenever there is an incomplete reaction, which is almost all of the time in industrial processes or in real life applications. So how do we define conversion? The conversion tells us how much reactant was consumed. To give you a benchmark, if we say that we have 100% conversion, that means that your limiting reactant was all consumed or was totally exhausted. So anything less than 100% conversion, that is already an incomplete reaction. So again, 100% conversion is a complete reaction. Anything less than 100% is already an incomplete reaction. Okay, so how do we define the conversion? In this case, we define conversion as a fractional value or a ratio between the moles reacted over moles fed. So how much or how many moles was reacted? It's simply the difference between the number of moles of the limiting reactants in the feed minus the number of moles of the limiting reactant in the output or in the product. So remember that it's moles reacted over moles fed. In this equation, we call this the fractional conversion because it's in the fractional form. If you want percent conversion, you simply multiply this ratio by 100%. Okay, let's try this example. For the oxidation of SO2, the fractional conversion of SO2 to SO3 is 0.65. Determine the outlet composition of a reactor if the inlet contains 30% SO2 and the balance O2. So let me first write the given. Okay, here are our given. We have the chemical equation SO2 plus O2 yields SO3. This is already balanced. And this is our representation of the reactor. Your feed to the process is 30% SO2 and 70% O2. Now, since these are all gases, we are going to be using percents by mole. The product is represented as having SO3 because that is our main product. It also has SO2 and O2 because the given conversion is 0.65. So let me just write it here. The conversion is 0.65, and as I have mentioned earlier, any conversion less than 100% signifies an incomplete reaction. Therefore, you always have some of your reactants present in the product. So they are unreacted reactants. Okay? Now let's represent these substances. In the product, SO3 is N1, SO2 is N2, and then O2 is N3. We are asked to find the outlet composition. Okay. This is an example of a typical material balance with chemical reaction problem. No? You are given the system, you're given a composition of the feed, you're given the conversion, and you're asked to find for the outlet composition. Let's first clarify what's this value of conversion pertains to. No? What species does it pertain to? So the 0.65 in this case, if we go back to the problem, if you carefully read this part, the fractional conversion of SO2 to SO3 is 0.65. Therefore, this value of conversion pertains to the direct conversion between SO2 and SO3. Why is this important? This is important because the value of the fractional conversion, if you are taking a look at oxygen to SO3, might be different. Because in this case, we are assuming that SO2 is our limiting reactant and oxygen is our excess reactant. The fractional conversion between the limiting reactant and the excess reactant is different. Okay, so you always have to clarify to which reactant does the conversion pertains. In this case, the conversion pertains to the limiting reactant. You can perform side calculations and confirm that SO2 is our limiting reactant. Okay, but in this case, let's now go to our solution. Let's set our basis because we cannot solve this without a suitable basis. We are given a composition in the feed, therefore the basis should be in the feed. Let's have 100 moles of F as our basis. Then let's go straight to the balances. Or better yet, let's first consider the definition of the fractional conversion. So the conversion is 0.65. But based on the formula that I gave earlier, this is the moles reacted over moles fed. It always pertains to the limiting reactant unless otherwise stated. So this is the moles of SO2 reacted divided by the moles of SO2 fed. And then the moles of SO2 reacted is simply the number of moles of SO2 going in minus the number of moles of SO2 going out over the number of moles of SO2 going in. With that definition of the fractional conversion, let's see if we can get something. So substituting, we have 0.65 is equal to SO2 in is 30% of the 100 moles, that's 30, minus out. The number of moles of SO2 going out is N2 divided by 30. So you see, given the value of the conversion, we are now able to solve for N2, or the amount of SO2 in the product stream. 30 times 0.65 and then 30 minus the answer. Okay, we have a value of N2, 10.5 moles SO2. So we now know how much SO2 is in the product stream. With this information, what could we do next? We could now proceed to our extent of reaction balances. Where should we start? We should start with the component with the most amount of given. In this case, it's SO2. Because we know how much SO2 is coming in, we were able to solve how much SO2 was coming out, so we can start with that. So what is your SO2 balance in terms of extent? That is SO2 out, 10.5, is equal to SO2 in, 30. It's a reactant, so minus 2 times extent. The coefficient in the balance equation for SO2 is 2. So we can now solve for the extent. What's our extent? That's 30 minus 10.5 divided by 2. 9.75 moles. Okay, next. Now that we were able to solve for the extent of reaction, it's now easier for us to determine the remaining components of the product. Let's begin with the SO3 balance. So what is your SO3 balance here? output, or the SO3 out, is N1 is equal to SO3 inputs, that's 0, there's no SO3 in the feed, and then plus, because it's a product, 2 times extent, 9.75. N1 is 19.5 moles SO3. Last one, oxygen balance. So oxygen out, that's N3. Oxygen in, that's 70 moles, 70% of the feed, minus extent, 9.75. $60.25. With that, we were able to determine the composition of the product. So of course, you still have to determine the percent by moles of the components of the products, but I will be leaving that to you. Okay? In the exam, if you're asked for a composition, you have to report either percent by mole, percent by mass, or mass fraction, mole fraction. Okay? You see here how we integrated the definition of the fractional conversion to the way on how we solve material balances using the extent of reaction method. Next. Selectivity. It is common for industrial processes to have more than one reaction occurring simultaneously. So this is applicable for both multiple reactions happening in series and in parallel. No? The selectivity here is defined as the number of moles of the desired products over the number of moles of undesired products. So in an industrial setting, if you have a very high value of selectivity, that means that you are maximizing the production of your desired products and you are minimizing the production of the undesired products. Okay, example. Ethylene is produced by the dehydrogenation of ethane. You're given the chemical equation C2H6 yields C2H4 plus H2. However, the produced ethylene can further react with excess ethane to form propylene and methane. If 100 moles per minute of ethane enters a reactor, the conversion of ethane to ethylene is 0.72 and the selectivity is 3.5. Determine the outlet composition of the reactor. So let me first write the given. Okay, here's our given. So we have the reactor with a 100 moles per minute feed, which presumably contains pure ethane as stated in the problem. We have two reactions. You see here I have listed. The first reaction is the main reaction, which is our desired. So in this case, our desired product is the ethylene. So I'm just going to mark the ethylene as D. This is the desired product. The second reaction pertains to the side reaction which was undesired or which we don't want to happen, or at least we want to minimize. No? So therefore, I will assign the C3H6 as my undesired product. You can also assign the CH4 as the undesired product. No? They're just the same. So basically, we are saying that we want to obtain C2H4 or ethylene, and we don't want to obtain C3H6 or propylene. Let's begin. By the way, we are also given values for the conversion from ethane to ethylene. That's 0.72, and the selectivity is 3.5. So as discussed earlier, selectivity is the number of moles of the desired products over the number of moles of the undesired. So it's like saying that the selectivity is the number of moles of C2H4 in the product stream, of course, over the number of moles of C3H6 in the product stream as well. In the diagram, I have left the composition of the product as blank because I want to clarify with you what should be in the product. So let's try to analyze. First, you should list everything that's in the product side of the reactions. So we have C2H4, H2, C3H6, and CH4. All of these are products. So now, even though C3H6 and CH4 are undesired products, they would still appear in the product side because they are being produced even in small amounts. Okay. Now, this is still incomplete. We should also include the reactants. In this case, our reactants are C2H6 for the first equation. For the second equation, we also have C2H4, but C2H4 is already a product of the first equation. No need to list C2H4 twice. Okay, this is sufficient. Now, since we want to determine the outlet composition, let us label your unknowns. We simply write N1, N2, N3, N4, and N5. So this is quite a long computation. We need to determine 5 amounts, but this will just be easy because you're already given the conversion and the selectivity. So let's begin. First, basis. The basis for this problem would be based from the feed. Let's have 1 minute operation. Next, let's take a look at the definitions for selectivity and for conversion. Let's start with conversion. So for the conversion, the value is 0.72. The conversion is defined as the number of moles reacted over the number of moles fed. So it pertains to our reactants, ethane. So the number of moles fed is in minus out. In is 100. Out is N1. Remember, because out is N5 over in. Conversion is in minus out over in, and this always pertains to the limiting reactant. In this case, it's C2H6. It's our only reactant. So from this definition of the conversion, we can readily solve for N5. So N5 here is 0.72 times 100, and then 100 minus the answer. So that is 100 minus 72. 28. N5 is 28 moles. And N5 is C2H6. Okay, so now that we have that, let's take a look at the selectivity. So the selectivity is the number of moles of C2H4. Remember, for the selectivity, you substitute the variables that are in the product side. Okay, so the number of moles of C2H4 in the product is N1, and the number of moles of C3H6 in the product is N3. This is equal to 3.5. So we don't know N1 nor N3 yet, so we will just have to set aside this equation. I'll call this equation 1, and this might be useful later when we perform our extent of reaction balances. Okay, speaking of, let's now perform the extent of reaction balances. Okay, what do we have? We will start with C2H6 because that is the component wherein we already have the value of the input and the output. However, take a look at our equations. By the way, I forgot to mention that those equations are already balanced. Okay? Now, since we have two different chemical equations, it's also imperative that you have two values of extent. I will just be representing them as extent 1 and extent 2. So why is this necessary? Remember that our extent of reaction balances are based on the components, and some components will appear on both equations. Example is C2H6. C2H6 appears on the reactant side of the first equation, and it also appears on the reactant side of the second equation. What would happen on our extent of reaction balance is it would just get longer. If you will remember the term plus minus coefficient times extent of reaction, that would just be doubled in this case because C2H6 appears on both equation 1 and equation 2. So let me show you. Let's perform the extent of reaction balance for C2H6. That is out. C2H6 output is N5, that is 28, is equal to in, that is 100. And then, from the first equation, C2H6 is a reactant, so that is minus extent 1. From the second equation, it's still a reactant, so that is minus extent 2. So we are performing the same extent of reaction balance, but we are just extending it to incorporate both equations. Okay? Since we don't know yet the values of extent 1 and extent 2, I will call this equation 2. Let's perform another balance. What balance would be useful for us? Let's see. Let's try to perform the C2H4 balance. So C2H4 is a product on the first equation, while it's a reactant on the second equation. So what should that balance look like? The outlet C2H4 is N1 is equal to input 0. There's no C2H4 at the feed. On the first equation, C2H4 is a product, so that is plus extent 1. On the second equation, it's a reactant, so that is minus extent 2. We will call this equation number 3. So how many are our unknowns? Extent 1, extent 2, and N1, and N3. Okay? So let's try to perform another balance. Let's have the C3H6 balance. So C3H6 only appears on equation number 2. Output is N3. Input is 0. There's no C3H6 on the feed. And then it's a product, so that is plus extent 2. Basically, we are saying that N3 is equal to extent number 2. This is our equation 4. Now, count our unknowns. Our unknowns are N1, N3, extent 1, extent 2. And count our equations. We have 4 equations, therefore we can solve this. To make this a 2 equations, 2 unknowns, we will have to substitute some equations for this to be simpler. So I will be using the selectivity equation as our base. So that is 3.5 is equal to N1 over N3. And then let's just substitute equations for N1 and N3. So first, N1, we can find N1 in equation number 3. So let's substitute. So we substitute 3, and N3 would be coming from equation 4. So let's substitute those both in equation number 1. We have 3.5 is equal to extent 1 minus extent 2 over N3 is extent 2. This equation simplifies to 3.5 extent 2 is equal to extent 1 minus extent 2. The extent 2 can be transposed to the other side of the equation. So let's transpose this one to the other side. This will now become 4.5 extent 2. I'll call this equation 5. Now we have used equation 1. We have used equations 3 and 4. We substituted them to 1. So therefore we can now, we can only use those that haven't been used for substitution. So that is equation number 2. We substitute equation number 5 to equation number 2. So substitute 5 in 2. What do we have? We have 28 is equal to 100 minus extent 1 is 4.5 extent 2 minus extent 2. And then the last two terms can be added together. So we have minus 5.5 extent 2. So this is now 72. Negative 72 is equal to negative 5.5 extent 2. We solve the value of extent 2 as 72 divided by 5.5. So that is 13.1. Now that we have the value of extent 2, we can substitute this to equation number 5 to solve for extent 1. So extent 1 is 4.5 times extent 2. Value is 58.91. Okay? Now, this should make sense that extent 1 is larger than extent 2 because remember, our desired equation is equation number 1 and equation number 2 is just a side reaction that is undesired. So therefore, it should make sense that extent 1 or the extent of the first reaction is larger than the extent of the second reaction. Okay, now that we already know the values of extent 1 and extent 2, so let me just list them here. Extent 1 is 58.91 moles. Extent 2 is 13.1 moles. Now that we have those values, we can go back to the extent of reaction balances and solve for the missing variables. Let's start with, by the way, we're done with N5. Okay, let's start with N1. So let me first erase some things. Let's go back to the C2H4 balance. Okay, so what is your C2H4 balance? Output is N1, input is 0. On the first equation, C2H4 is a product, so that is plus extent 1. Second equation, reactant, so minus extent 2. Substitute, we get a value of, so it's just extent 1 minus 2. So 58.91 minus 13.1. That is 45.81 moles C2H4. So we're done with N1. Next, N2, you perform a water balance. Okay, output is, sorry, it's not H2O, it's just H2 balance. Output is N2, input 0. And it appears on the first equation only as a product. So this is plus extent 1. Therefore, N2 is 58.91 moles H2. Okay, next, N3. For N3, you have two choices. Either you perform the C3H6 balance or you go back to the definition of the selectivity, this one, wherein we already have the value of N1, therefore we can get N3. So N3 is simply N1 over 3.5. Then this, so N3 is, N1 is 45.81 divided by 3.5. Okay, 13.09. This is moles C3H6. Okay, last one, N4. We perform a CH4 balance. So a CH4 balance is output N4, input 0, plus extent 2. Okay, CH4 only appears in the second equation at the product side. So N4 is equal to 13.1 mole CH4. We have completed the values for the components of the product. What's left for you to do is to simply gather all of our results, take the total number of moles, and then convert this composition into percent by mole or mole fraction. Okay, next. We now have demonstrated the basic skills needed to solve a material balance problem with chemical reaction. No? So you just have to remember how to perform the extent of reaction method. You simply remember the concepts of conversion, percent excess, and the number of theoretical moles. No? And with that, you are now ready to solve some problems on your own. Now, I have here 3 more examples. Okay, so these 3 examples will be part of your worksheet number 5. Okay, In these problems, while you are solving them, if you encounter any difficulty, feel free to message me in Messenger so that I can help you solve these problems. You just follow the given examples earlier and then apply the concepts here. Okay, so that's it for this lecture. I hope you have learned something. If you have any questions, don't hesitate to ask me, and as always, keep safe.